Today's video is about two things, really. One is about measurement and how we can carefully take measurements of some physical quantities. And the second thing is about a concept called density that lots of people have heard of before, and some people think they know what that means, but there's a lot of misunderstanding about it. And we'll approach it from a different way than we normally think about density, and hopefully that will solidify your understanding of what density really is. Our objective here is to find the volume of this wooden block and then compare it with its mass. To find the volume of the wooden block, because it's a rectangular solid, we need the thickness, the width, and the length. So let's do those measurements. Here's our thickness. Width. And now let's measure the length. And now let's find the mass of the wooden block. Now we have more wooden blocks that have the same thickness and width because they were cut from the same stick of wood. So we only need to measure the lengths of these. There's the length. How's the mass of that block? Length. Now the mass. Length. And now the mass. Length of this block. And now its mass. Now we're going to find the thickness, width, and length of aluminum blocks. There was the thickness. Here's the width. And now the length. So that should allow us to calculate the volume of the aluminum block. I'll find its mass. The rest of these aluminum blocks have the same thickness and width, so we need to only measure their lengths and masses. There's the length. And there's the mass. Length. And a mass. Length. And mass. One more. Length. And now let's find its mass. Now we're going to measure the volumes of some samples of liquid. Got this blue liquid. This is sample number 1. It's in this thing called a graduated cylinder. There are markings on here. Every marking is 0.2 of a milliliter. There's the the volume. There's number 2. Adjust the camera angle so that we're getting a nice straight-on look at the volume measurement every time. There's our volume. Sample number 3. There's our volume. Fourth sample. Fifth sample. This will be the last one. Adjusting the camera angle a little bit so we can get a better reading. There's the volume. Now we're going to find the masses of each of those liquid samples. There's number 1. Number 2. Three. Number 4. And the last one, number 5. Here's a spreadsheet that has all the data on it that we just took. You can see that for the wood on the top here, we have the width, the thickness, and the length. There's an open column for volume. We'll have to calculate that. And then here are the masses for each of those wooden blocks. Same thing for the aluminum. That's duplicated right here. The width, the thickness, the length, open spot for volume, and then mass. And then the blue liquid, volume is listed, and then the mass. We don't have to do any calculations because we measured the volume directly. Let's calculate the volume. This is pretty easy to do on a spreadsheet like this. Just make a formula by putting an equal sign. And I'm going to point to the length times the thickness times the width. And when I hit return, it calculates that volume in cubic centimeters because it was centimeters by centimeters by centimeters. So cc's for short. On a spreadsheet, you can usually copy these formulas pretty easily. And so I'll do that. And I'm going to copy this formula down here and calculate the aluminum volumes just like that. Okay, so now I have volumes and I have masses. Now let's analyze this data by using vernier graphical analysis. I'm going to pop this open. And we're going to do manual entry, so I'm just going to click that. And I want to have both of these windows available at the same time so I can transfer the data over. So I'm going to shrink this window down a little bit. To make room for my graphical analysis, which I'm also going to have to shrink just a little too. There we go. All right, so the first data set is going to be where we put our wood data. So I'm going to rename this data set. Instead of generic data set 1, I'm going to put wood in here. The horizontal axis is going to be the independent variable, which is the volume. So I'm going to click column options, and I'm going to change from X to volume. The unit we were using is cubic centimeters, cc's. Now click apply. The vertical axis, the dependent variable, that is the mass. And we were measuring that in grams, so I'll put a G for that. Now it's time to just enter some data. And I'll probably speed this up because it's pretty boring watching people type numbers. You can see as I typed, it created a scatter plot, and this looks like it's a straight line. Let's do regression analysis and just find out if we're right about that. I'll click Apply Curve Fit and then choose Linear. And sure enough, our R value is very high, 0.9992, indicates that the relationship between the mass and the volume of these wooden blocks appears to be linear. Let's do the same thing for aluminum. I'm going to add a new data set. I'm going to name this one aluminum. And it already puts the headings on here, volume and mass, because those are the things that I'm entering here. So I'll just enter numbers. Once again, it looks like a straight line relationship works. Let's check it out by applying a linear curve fit. And again, very good R value. Now let's add the blue liquid. New data set. We'll name this blue liquid. And enter our data. Okay, here's our graph. Again, it looks like a straight line relationship. Let's change something. Change a few things. First of all, let's make our vertical and horizontal axes appear on the graph by making our left axis range, x-axis range, a -1, and our bottom y-axis range also a -1 so that the axes show up. And let's click here and let's turn on the wood and the aluminum as well as the blue liquid so we have all of our graphs on the same graph, all of our scatter plots on the same graph. And let's do linear analysis for all of them at once if we can. So we'll apply curve fit linear for all of them. Click apply. And here's what we find. The wood blocks, that's in red here, have the least steep slope. The slope is 0.4513. Let's think about the units of slope. It's grams for every 1 cubic centimeter. The blue has the steepest slope. That's 2.81 grams for every 1 centimeter, 1 cubic centimeter. And then in between is the blue liquid. The blue liquid has a slope of about 1.0 grams for every cubic centimeter. The slope of this graph of mass against volume is what we call density. Density is a comparison of how much one specific unit of volume weighs. So density isn't the same as mass. It's possible for a wooden block to weigh more than a piece of aluminum if it's a bigger wooden block. But the density, the ratio of mass to volume, will always be lower for a wooden block and higher for aluminum. Here's another interesting thing about this graph. We notice if we sort of trace where the blue and red lines are going to, that they seem to cross the horizontal axis at about the 0 mark. But the blue liquid line doesn't. It crosses at about the 7 grams maybe mark. And there's a reason for that. If you think about it, the slope tells how much you increase the mass when you increase by a specific volume. But the vertical intercept, that starting point on the line, that represents what is the mass when you have no volume. When you have no volume of a wood block or no volume of an aluminum, that means you just don't have any of it at all. When you have no volume of a blue liquid, you still have the empty container. So we can use this graph as a way of figuring out what is the mass of that empty container. It looks like it's about 7 grams. Let's take a look at a physical meaning of the different slopes of these graphs. Here I have a beaker of the blue liquid that we used in the experiment. Here's an aluminum block. When I drop it in, the aluminum block sinks to the bottom. Here's my wooden block. When I put it in, it floats on the top. So things that have a steeper slope, which are more dense, will sink in things that have a less steep slope.